Hi, I'm Julia Baker, and I am presenting on behalf of myself and my co-scholars Kim Nguyen and Kirby Yamamoto. We worked with Andre Perez at the Center for Animal Health and Food Safety on the parameterization of a COVID-19 model in the epidemics platform designed by collaborators at Epi Interactive. The epidemics COVID-19 model is a deterministic state transition epidemiological model. So an expansion of the classic SIR infectious disease model. It has 6 compartments listed here and allows the user to define a wide number of parameters, a few of which I have listed down below. This summer, during Summer Scholars, we first learned everything we could about what goes into the black box of equations that actually makes up a model, because all 3 of us were complete novices. Once we had the basics down, we began asking questions using the epidemics model, like what do the first 100 days of an outbreak look like in a hypothetical population? And then we began to look at modifying the inputs of the model and looking at how it changes. So as we modify R naught, the efficacy of social distancing or the efficacy of isolation, what changes? And how do we quantify the changes that we see in the outbreak dynamics? What specific outputs are key that we should watch? In this case, our hypothetical population was 5.64 million people, or the rough population of the state of Minnesota. And we ran a variety of simulations, each 100 days long, and modified some inputs to see what changed. So here we have on the left-hand column the parameters that we modified from R naught, which was 2.68 to 3.78, which covers a range of values published from hotspots around the world. And then the efficacies of social distancing and isolation of clinical cases, we ran in increments of 10%, from 0 to 0.5 in the case of social distancing, and from 0 to 1 in the case of efficacy of isolation of clinical cases. We chose to monitor cumulative deaths at day 100 and the day with the peak number of infectious cases as markers for changes in outbreak dynamics. Here on the right-hand side, you can see extremes of the scenarios run. We only reached 50% efficacy of social distancing because we sort of maxed out, meaning the outbreak decreased in severity and the delay of the pandemic was pushed beyond the 100-day end of the model scenario. As you can see, we reached 100% efficacy of isolation of social distancing, and we're approaching kind of that same max out point that we reached with the social distancing. So what did we find by running all these different scenarios and watching our key outputs? What we found is that we confirmed that this model is sensitive to all 3 of the parameters modified, meaning as we change those inputs, the outputs do change. This is important. Sensitivity to changes in R naught is necessary so that the model has utility for distinct outbreaks, because R naught is different in each individual hotspot. Additionally, we found that this model was sensitive in different degrees. It was more sensitive to changes in the efficacy of social distancing than it was to changes in efficacy of clinical isolation. So what we tried to show here is that these models can help us ask questions regarding the relative intensity and speed with which outbreaks unfold. We can ask questions using these models to investigate how these dynamics might change. For instance, what effect do superspreader events have? Or how do mask mandates or vaccination campaigns change the dynamic outcomes? Models like the epidemics COVID-19 model can help us explore these what-if scenarios to better understand these outbreaks and control strategies used to mitigate them. Thank you for listening. Please direct any questions to the emails listed here.